Various devices are employed in the design of a vehicle's driving system to ensure safe and comfortable driving. One of them is the wheel alignment to adjust the angle when installing the tires. Now let's take a close look at the tires and wheel alignment, which have a great influence on a vehicle's performance in straight driving and turning. A car has to be able to respond appropriately to various situations. It should provide a stable ride along a straight road, corner smoothly, and return safely and efficiently to a straight course after cornering. So wheels are fixed to the body of a car at certain angles to obtain the desired effects. The combination of these angles is called the wheel alignment. The front wheel alignment is made up of 5 factors: camber, caster, steering axis inclination, toe angle, and turning radius. Let's see the role of each factor in turn using a model. When you look at a vehicle from the front, you can see that the wheels are fixed with their tops tilted outward or inward. This is called camber and is measured in degrees of tilt between the tire center line and the plumb line. When the top of the wheel is tilted outward, it is called positive camber. When it leans inward, it is called negative camber. When the camber is 0, the load on the spindle is applied at the tire's center line and the point where the spindle intersects. Giving the wheel a positive camber causes the load to be applied to the inner side of the spindle, reducing the force which might bend the spindle and steering knuckle. The vertical load from the road F is divided into force F1, which is vertical to the axis of the spindle, and force F2, which is parallel to the axis of the spindle. F2 forces the wheel inward, helping to prevent the wheel from slipping off the spindle. In some suspension systems, the load on the axles makes the tops of the wheels tend to tilt inward. So giving the wheels positive camber helps to prevent this. Usually, for these reasons, positive camber was commonly employed on most vehicles. However, recently improvements in such things as suspension performance make the need for positive camber less, and the employment of wide tires makes 0 or negative camber standard. Now let's take a look at the role of negative camber. Let's have a look at a simple experiment. When you make a tire stand on its rim and push it, the tire rolls forward in a straight line. Now let's roll the tire tilted, in other words, with camber. As you can see, the tire curves in the direction of its leaning. This is called the camber thrust. When a vehicle is cruising straight, it is important for the tires to transmit the driving force directly to the road surface, making contact with the road surface at right angles. On the other hand, when a vehicle is cornering, the wheels on the outside of the turn tend to acquire a positive camber. This is especially true with independent suspension because centrifugal force causes the load to shift outward. When this happens, a heavy load is applied to the tires on the outside of the turn due to the centrifugal force. Then, as you can see from the previous experiment, camber thrust acts on the outside tires in the opposite direction to that of the turn, degrading cornering performance. So the aim of giving the wheels negative camber is to ensure that the tires grip the road surface properly, even while cornering, improving cornering performance. Caster refers to the tilting angle of the steering axis, viewed from the side, and is shown with the angle from the plumb line. A backward leaning is called positive caster. However, hardly any vehicles feature negative caster. For positive caster, the point at which the steering axis center line intersects the ground is more forward than the center at which the tire makes contact with the road surface. The distance between these two is called the caster trail. Let's examine the role of caster and caster trail using only one wheel of a cart. As you know, when you push a cart fixed with this kind of caster, the cart moves straight, smoothly in the direction as pushed. In this case, the steering axis is not tilted. However, caster trail occurs because the center of wheel-to-road contact comes behind the steering axis. This figure shows the composite force acting at the wheel-to-road contact area, represented by the circle. The tire friction at the center of the wheel-to-road contact area opposes the forward-acting force by the trail amount. This provides stability while driving straight. When this principle is applied to an automobile, two wheels should be considered at the same time because the left and right front wheels are connected. In this experiment, the model stands vertically and the wheels are secured so they do not rotate. Weights equivalent to the friction are attached. First, the caster angle is 0. Turn the steering wheel. As you can see, after the wheel is turned, the wheels remain in the position they were turned out. Looking at the forces acting on the wheel-to-road contact area, it works like this. If A and A' are the steering axes when the wheel is turned, the arrows show the rolling resistance of the wheels. When turning the steering wheel from the straight-ahead position to the left, the moment functions on the right wheel to pull it back to its original straight-ahead position. The reverse but equal size of the moment which functioned on the left wheel balances this force, and the wheels remain where they are. Now a caster angle is introduced. Let's turn the wheel to the left in the same way as before. As you can see, the left and right wheels swivel back to their original straight-ahead condition automatically. This figure demonstrates that the points A and A' where the extension of the steering axis intersects the ground shift forward by the amount of caster trail because the caster is applied. When the steering wheel is turned, the moment functioned on the wheel on the outside of the turn is large, while the moment functioned on the wheel on the inside of the turn is small. As a result, a force is applied to swivel the axle back to the straight-ahead position where these moments balance. This force makes straight-ahead driving stable. This straight-ahead stability is created by the caster trail. The positive caster also results in straight-ahead stability because of the caster angle itself. The reason can be explained using a model. Without a caster angle, if the steering wheel is turned, no wheel recovery force is produced because the wheels are turned on a plane surface. With a caster angle, on the other hand, when the steering wheel is turned, a jack-up torque is generated at the wheel on the inside of the turn, raising the car body. If you release your grip on the steering wheel after turning, the weight of the car applies wheel recovery force, and the steering wheel swivels back to the straight-ahead condition where the moments on the left and right wheels are balanced. So as we have seen, positive caster and caster trail contribute to straight-ahead stability and wheel recovery after turning. Steering axis inclination is the angle between the steering axis and the plumb line as viewed from the front of the car. It is also called the kingpin angle. The distance between the intersection of the steering axis with the ground and the wheel center line with the ground is called the offset or scrub radius. Suppose the steering axis is vertical and camber is 0. In this case, the offset is large, so the vehicle turns in a large arc when the wheel's direction is changed. Because of the greater friction generated by the turning wheels, a greater effort is required to steer. On the other hand, if the steering axis is tilted and the offset is reduced, the wheels can turn in a smaller arc. This can reduce the effort needed to steer. Thus, one role of steering axis inclination is to make steering easier. When the wheel is subject to shocks caused by irregularities in the road surface, or when braking force is applied to the wheel, a moment is generated with the radius of the offset. The influence of this force on steering can be reduced by making the offset small. Moreover, when there is a steering axis inclination, the wheel raises the car body during cornering, geometrically increasing the effect of the wheel recovery force of a caster, as explained earlier. So steering axis inclination also contributes to increased straight-ahead stability. When you look at a vehicle from above, the left and right wheels are not installed pointing straight forward, but are angled slightly. As you can see, when the front of the wheels are closer together than the rear, this is called toe-in. The opposite arrangement is called toe-out. The main function of toe angle is to cancel out the camber thrust generated by camber. Let's see the case when the front wheels are given positive camber and the toe angle is 0. As the wheels tilt outward at the top, they try to roll outward as the car moves. So the wheels are given toe in to cancel the tendency to roll outward caused by the camber. As vehicles have recently started featuring a camber approaching 0, the toe angle value is also becoming smaller. Turning radius refers to the turning angle of the left and right front wheels during cornering. By making the turning angle of the left and right wheels different, the four wheels of the vehicle turn around the same center. If the angles for the left and right front wheels were the same, each wheel would turn around a different center. So side slipping of the tires would make smooth turning impossible. In order to solve this problem, the wheel inside turn is given a larger turning angle. Thus, the turning radius is made smaller, so that the center of the turn is the same for each wheel and is in alignment with the rear axle center line. This is the turning radius. Usually, the term wheel alignment is used to refer mainly to the alignment of the front wheels. However, total four-wheel alignment, including rear-wheel alignment, has become important because of the recent increasing demand for more sophisticated driving performance. For example, even if the alignment for each of the four wheels is normal, straight-ahead stability will be reduced when the front and rear axles are not parallel. Even if the axles are parallel, a lateral misalignment will lead to a difference in left and right cornering. So you need to be comprehensively sure that each of the four wheels is properly aligned to the car body. It is especially important to check the four-wheel alignment of a vehicle which has been in an accident. Now let's see the actual wheel alignment procedure. First, check the following points. Check the tires for improper size, wear, deformation, and improper inflation. Check suspension and steering linkage for looseness. Check the tires for runout using a dial gauge, and confirm that the radial runout is less than 1.0 millimeters and lateral runout is less than 1.2 millimeters. Check that the shock absorbers function properly by performing the standard bounce test. Check the chassis to ground clearance and confirm that it is within specification. After finishing checking, camber, caster, and steering axis inclination are inspected. Various types of gauges are available, but here this camber caster kingpin gauge is used. With the turning radius gauge locked, place the front wheels on the gauge so that the tire center line and the spindle center line are aligned at the center of the gauge. Now place stands of the same height as the gauge under the rear wheels to keep the vehicle level. Next, remove the wheel cap. Then remove the cotter pin and nut cap. Then fully tighten the gauge adapter by hand. And attach the camber caster kingpin gauge. The inspection should be carried out with the vehicle empty and the front wheels locked, so depress the foot brake using a brake pedal pusher. To prevent the battery from discharging while you are doing this, remove the brake light fuse so that the brake lights will not light. Then release the turning radius gauge lock. Measure the camber. Camber is the wheel's inclination as viewed directly from the front of the vehicle. Measure the angle made by the wheel's center line and the plumb line. With the wheels in the straight-ahead position, align the air bubble on the level with 0. Take a reading of the air bubble scale of the camber measuring gauge. Next, measure caster and steering axis inclination. Caster is the inclination of the steering axis as viewed from the side, and steering axis inclination is the inclination as viewed from the front of the car. Measure the angle from both verticals. When measuring the right front wheel, turn the wheel to the right by 20 degrees. Use this as the reference. Then turn the wheel to the left by 20 degrees and take readings of the scale. For the left front wheel, turn the wheel to the left by 20 degrees and use this as the reference. Then turn the wheel to the right by 20 degrees and take readings of the scale. Let's take the right front wheel as an example. Turn the wheel inward by 20 degrees on the turning radius gauge. Turn the adjusting knobs on the back of the gauge and align the air bubbles for the caster measuring gauges to 0 on the scale. Then align the air bubble for the steering axis inclination measuring gauge for the right wheel to 0 on the scale. After setting the gauge, turn the wheel in the opposite direction by 20 degrees from the straight-ahead position. Take readings of the respective air bubble scales for caster and steering axis inclination. Measure camber, caster, and steering axis inclination of the left front wheel in the same way. Next, measure the turning radius. The turning radius is the turning angle of the wheel when the steering wheel is turned as far as it will go. The angle from the straight-ahead position is measured for the left and right directions. This measurement should be performed by 2 people. Turn the steering wheel clockwise as far as it will go and take a reading of the turning angle with the turning radius gauge. In the same way, turn the steering wheel counterclockwise and take a reading of the turning angle. Measure both right and left side wheels in this way. Next, measure the toe angle. Toe angle refers to the distance between the fronts and rears of the wheels when the vehicle is viewed from above. For the toe angle measurement, the angle is not measured. Instead, the distance between the tire center lines is measured at the front and the rear of the tires, and the angle is determined by calculating the difference. Bounce the vehicle up and down to stabilize the suspension. Move the vehicle forward about 5 meters with the front wheels in the straight-ahead position on level ground. Do not move the vehicle backwards until the measurement is completed. Take the measurements only with the vehicle on an absolutely level area. Put a mark in the center of the tread on the rear of each front tire and measure the distance between the marks. The mark should be made at the same height as the spindle. Then move the vehicle forward until the marks on the rear of the tires come to the height of the gauge placed in front of the tires. If the tires roll too far, do not move the vehicle back. Move the vehicle forward another 5 meters and start again. Measure the distance between the marks in the front of the tires. Then calculate the difference between this figure and the distance measured on the rear of the tires. If toe in or toe out are not within specification, adjust them. To make an adjustment, remove the boot clips and loosen the tie rod and lock nut. Turn the left and right tie rod ends an equal amount to adjust the toe in and toe out in accordance with the specification given in the repair manual. One way to make an overall evaluation of wheel alignment is to measure the side slip amount of the left and right tires with the side slip tester. The side slip tester detects the sideways slip amount when the wheels cross over the laterally moving plates. Let's see how to do this. Drive the vehicle slowly in a straight line onto the side slip tester. Then read the side slip indication as the wheels cross over the tester. Side slip is the amount of sideways slippage expressed in millimeters per 1 meter of forward motion. If the side slip exceeds the limit, camber and toe angle may not be correct. If so, another inspection is needed. Now let's take a look at tires, which play an important role in ensuring a safe, comfortable ride. Tires are the only components of the vehicle that come into direct contact with the road surface. Tires have 4 functions: to support the whole weight of the vehicle, to transmit the vehicle's driving and braking forces to the road, thus controlling starting, acceleration, deceleration, stopping, and turning, to reduce shocks caused by irregularities in the road surface, and to change the vehicle's direction. The basic components of a tire are its carcass, bead wires, breaker or belt, and a rubber layer which covers the surface. The rubber layer consists of tread, shoulder, sidewall, and bead. The carcass can be regarded as the framework of a tire. A number of cords made of polyester, nylon, or steel are arranged in parallel. Then thin rubber film is stuck on each side. These sheets are stuck together and molded into the form of a tire. In a radial ply tire, these cords are arranged in a radial manner to form the framework of the tire. In a bias ply tire, these cords are arranged diagonally and stuck together in alternate layers to form the framework of the tire. A fiber layer called breaker is provided on the outer surface of the carcass. This strengthens the adhesion between carcass and tread and reduces shocks transmitted from the road surface to the carcass. The tread comes into direct contact with the road surface and transmits the driving and braking forces to the road. It protects the carcass from wear and shocks caused by the road surface. A wide variety of tread patterns are molded on the surface to transmit the forces effectively to the road. The sidewall is a rubber layer covering the flank of a tire. It protects the carcass from external damage. Bead wires and the beads secure the tire to the rim. The size of a tire is indicated by letters and figures on its side wall. This is one example. The first figure shows that the tire is 195 millimeters wide, and the next figure, 70, represents the compression. Compression is the ratio of the height to the width of the tire expressed as a percentage. The letter R indicates the tire structure. In this case, the tire is a radial ply type. 14 shows that the tire fits a 14-inch diameter rim. 91 is a load index, showing the maximum permissible load for one tire. The letter S at the end is a symbol representing the maximum permissible speed. The disc wheel functions as a frame to maintain the shape of the tire. It also supports the whole weight of the vehicle, driving and braking torques, and lateral forces generated during cornering. So a disc wheel must be strong enough to withstand these forces. For a comfortable ride and for the tire to have optimal grip on the road surface, the disc wheel must be light. It must also have an exact shape and precise dimensions. A disc wheel consists of a rim for keeping the tire in place and a disc for fixing the disc wheel to the hub. The size of the disc wheel is represented by the rim diameter, rim width, and the shape of the flange. In this example, the rim diameter is 14 inches, rim width is 5.5 inches, the shape of the flange is of the J type. Other precautions which should be taken in the size of the disc wheel are the offset and PCD. The offset is the distance between the center line of the disc and the surface which is fitted to the axle hub. Using disc wheels of different offsets would cause a number of problems arising from changes in the vehicle's tread or the tires coming into contact with the brake caliper. PCD means the diameter of the circle made when the centers of the bolt holes are connected. Different automakers and vehicle types have different PCDs, and it is impossible to use disc wheels with different PCDs. Ideally, a tire's circumference should be perfectly round, and the tire should be homogeneous and balanced as a whole. However, actual tires tend to be uneven to a certain extent because of their structure. This can cause vibration and noise while driving. Imbalance arises from three factors: weight distribution, dimensions, and rigidity. The most common factor among these is the lack of wheel balance. Wheel balance is sorted into static balance and dynamic balance. First, let's see the static balance. Using this model, make a disc turn. In this case, it rotates smoothly because it is balanced. A particular point on the disc can stand still at any position. Now what happens if a weight is attached to a part of the disc? In this case, vibration is produced because the centrifugal force of the heavy part acts on the disc. It always comes to a stop with the heavier portion at the bottom. The disc is statically unbalanced. In order to correct this imbalance, a matching weight is attached to the point diametrically opposite to the weight attached earlier. As you can see, the vibration problem is eliminated and the disc rotates smoothly. Now let's see the dynamic balance. The tire has thickness, So let's suppose that heavy spots are located inside and outside the disc assembly. In this case, the disc assembly can stand still at any position. In other words, the disc assembly is statically balanced. On the contrary, when the disc assembly is turned, the points where the centrifugal force acts on the heavy spots are different, so vibration is generated as a result. A wheel in this condition is dynamically unbalanced. In order to correct this imbalance, a weight is attached to the point diametrically opposite the heavy spot, both outside and inside the disc assembly. As you can see, the vibration problem is eliminated and the disc assembly rotates smoothly. This state is called wheel balance. On an actual automobile, balance weights like these are attached to achieve wheel balance. Runout is defined as an imbalance in tire dimensions. There are two types of runout: radial runout, measured along the tire's radius, and lateral runout, measured along the axle. When a tire with large radial runout is rotated, it raises and lowers the automobile with each rotation. As the vehicle's speed increases, the tire vibrates the body of the car and the steering wheel. Lateral runout will lead to abnormal tire wear and an unstable ride. Another tire imbalance problem that occasionally crops up is a flat spot. If a vehicle is parked for an extended period of time with its tires warm after driving, the portion of each tire that is in contact with the ground will become flat. In general, this problem disappears spontaneously after driving the car a little, as the tire temperature increases. Now let's see the inspection and maintenance when tires are causing vibration. First, check that the wheel center is aligned with the hub center. Using the thickness gauge, inspect the hub-to-wheel clearance along the entire circumference. If the clearance difference exceeds 0.1 millimeters, adjust the position of the tire and refit it at the position with the least difference. Next, check the runout of tires. To eliminate the influence of a flat spot, put the car on the lift immediately after running it and leave it for 10 to 15 minutes. Adjust the tire inflation pressure to the standard pressure. At the same time, remove any foreign objects which may be stuck in the tire tread. Touch the spindle of a dial indicator to the center of the tire tread at a right angle. Turn the tire slowly by hand and measure the radial runout. Then touch the spindle of a dial gauge at a right angle to a portion of the side wall of the tire which has no protrusions or indentations. Turn the tire slowly by hand and measure the lateral runout. If the measurements show the runout to exceed the target values, determine whether the problem lies with the disc wheel or the tire and replace whichever is defective. Next, check off the car balance. Put a register mark on the tire and then remove the tire. Confirm that the wheel balancer functions correctly before the check. Correct the static and dynamic balances by taking 0 gram as the target value. It is important to use and fit balance weights which match the wheels so that they do not fall off while driving. When wheel balance is attained, fit the tire back on the vehicle in accordance with the register mark you made earlier. Check again that the tire does not have run out. Then check on the car balance. On the car balance is checked with the wheel cap, valve cap, and center ornament attached. When correcting the balance of the drive wheels, turn the wheels with the engine started while increasing or decreasing the speed gradually. When the inspection and adjustment of each tire are finished, be sure to check the wheel alignment. This video has explained wheel alignment and tires, which play an important role for driving stability and comfortable ride. They have a direct impact not only on improving riding comfort and driving stability, but also on affecting safety. We hope you will strive to improve your work and technical knowledge by taking advantages provided by this video and other references.